Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 2018 marked a watershed moment in the annals of physics, awarding the Nobel Prize to Donna Theo Strickland and Gérard Albert Mourou for their groundbreaking invention of chirped pulse amplification. This innovation, more than a mere technological advancement, constitutes a fundamental paradigm shift in the generation of high-intensity, ultra-short optical pulses, reshaping fields ranging from fundamental physics to biomedical engineering. To appreciate both the elegance and the profound implications of this work, a journey through the intellectual landscape preceding its genesis, followed by a meticulous examination of its core mechanisms, immediate applications, and enduring influence, is essential. This also includes an honest appraisal of its reception and subsequent refinements. The quest for ever higher peak optical powers, a driving force in laser physics, encountered a significant obstacle in the inherent limitations imposed by the optical components themselves. Amplifying an ultra-short pulse directly to terawatt levels would inevitably damage or even destroy the gain medium and subsequent optical elements, primarily due to nonlinear optical effects induced by the intense electric field. Earlier attempts to circumvent this hurdle involved increasing the mode size within the amplifier, thereby reducing the intensity experienced by the optical components. However, this approach proved limited in its scalability and often resulted in a degradation of beam quality. Alternative strategies, such as using larger aperture amplifiers, proved prohibitively expensive. Therefore, a more ingenious solution was required. Strickland and Mourou's innovation, born from a blend of theoretical insight and experimental ingenuity, elegantly sidestepped this limitation. Chirped pulse amplification, or CPA, operates on a deceptively simple yet transformative principle, temporarily stretching the pulse before amplification, thereby reducing its peak power, amplifying the stretched pulse, and then compressing it back to its original duration. This stretch-amplify-compress sequence allows for the generation of extremely high-energy pulses without subjecting the optical components to damaging intensities. The initial step in CPA involves temporarily stretching the ultra-short pulse. This process, known as chirping, is typically achieved by passing the pulse through a dispersive element, such as a diffraction grating pair or a fiber optic cable with significant chromatic dispersion. These devices introduce a frequency-dependent delay, such that different spectral components of the pulse travel at slightly different speeds. This results in a temporal stretching of the pulse, with the redder lower frequency components arriving earlier and the bluer higher frequency components arriving later, or vice versa, depending on the sign of the dispersion. The resulting stretched pulse's duration may be orders of magnitude longer than the original, effectively reducing its peak power by a corresponding factor. The stretched pulse is then amplified in a conventional laser amplifier. Because the peak power is now significantly lower, the amplifier can operate without inducing nonlinear optical effects or causing damage. The amplifier gain medium can consist of a variety of materials, depending on the desired wavelength and pulse energy. Common choices include titanium-doped sapphire crystals and neodymium-doped glass. The precise characteristics of the amplifier, such as its gain bandwidth and saturation fluence, must be carefully matched to the properties of the stretched pulse to maximize amplification efficiency and minimize pulse distortion. Following amplification, the stretched pulse must be compressed back to its original duration. This is achieved by passing the pulse through a second dispersive element that introduces a delay opposite to that introduced by the initial stretcher. Typically, a diffraction grating pair aligned in a geometry complementary to the stretcher is used. The compressor effectively rewinds the chirping process, bringing all the spectral components of the pulse back into temporal alignment. Precise alignment and careful control of the grating separation within the compressor are crucial for achieving optimal pulse compression and minimizing residual temporal broadening or pulse shaping artifacts. In essence, the compressor undoes what the stretcher did, but only after the pulse has been amplified to significantly higher energy levels. The immediate impact of chirped pulse amplification was transformative. Prior to its invention, generating terawatt pulses from tabletop laser systems was a formidable challenge, largely confined to specialized research laboratories. CPA enabled the construction of compact and relatively affordable terawatt and even petawatt laser systems, democratizing access to high-intensity laser technology for a much broader scientific community. One early and particularly impactful application was in the generation of high-order harmonics. By focusing intense CPA-amplified laser pulses onto a gas jet, researchers could generate coherent radiation at extreme ultraviolet and soft X-ray wavelengths. This opened up new avenues for Toscund science, enabling the study of electron dynamics in atoms and molecules on unprecedented timescales. Another early application of CPA lay in laser-induced breakdown spectroscopy, or LIBS. By focusing a CPA-amplified laser pulse onto a sample, researchers could ablate a small amount of material and create a plasma. The light emitted by the plasma contains information about the elemental composition of the sample. LIBS became a valuable tool for rapid, non-destructive compositional analysis in a wide range of fields, including materials science, environmental monitoring, and homeland security. The influence of chirped pulse amplification extends far beyond these initial applications. The technique has become an indispensable tool in a multitude of scientific disciplines and technological applications. In fusion research, CPA-amplified lasers are used to compress and heat deuterium-tritium targets to initiate nuclear fusion reactions. The National Ignition Facility, a massive laser facility in California, relies on CPA technology to deliver the immense power required to achieve inertial confinement fusion. In medical imaging, CPA-based lasers are employed in optical coherence tomography, or OCT. OCT is a non-invasive imaging technique that uses low-coherence light to create high-resolution cross-sectional images of biological tissues. CPA allows for the generation of the ultra-short pulses needed to achieve the high temporal resolution required for OCT imaging, enabling the diagnosis of diseases such as macular degeneration and skin. In materials processing, CPA-amplified lasers are used for precision cutting, welding, and drilling of a variety of materials. The ultra-short pulse duration minimizes the heat-affected zone, resulting in cleaner and more precise machining. This has led to applications in the manufacturing of microelectronics, medical devices, aerospace components. Over time, chirped pulse amplification itself has undergone significant refinements and generalizations. One important development is the introduction of optical parametric chirped pulse amplification, or OPCPA. OPCPA utilizes nonlinear optical crystals to amplify the stretched pulse, offering several advantages over conventional laser amplifiers, including broader bandwidth, higher gain, and lower thermal loading. This has enabled the generation of even shorter and more powerful laser pulses. The amplification pathway in OPCPA relies on a three-wave mixing process. A pump beam and a signal beam, both with carefully selected wavelengths, interact within the nonlinear crystal. This interaction leads to amplification of the signal beam while simultaneously generating an idler beam. The efficiency of this process depends critically on phase matching, which ensures that the interacting waves propagate in such a way that their phases remain aligned, maximizing energy transfer from the pump to the signal. Furthermore, advanced pulse shaping techniques have been integrated with CPA to precisely control the temporal and spectral properties of the laser pulses. By manipulating the phase and amplitude of different spectral components of the stretched pulse, researchers can tailor the pulse shape to optimize specific laser-matter interactions. This capability has opened up new possibilities for coherent control of chemical reactions, selective ablation of materials, and advanced imaging techniques. Despite its overwhelming success, chirped pulse amplification has not been without its critiques and limitations. Early CPA systems suffered from limitations in pulse contrast, meaning that the amplified pulse was often accompanied by a significant amount of background light. This background light could interfere with sensitive experiments or damage sensitive samples. Over the years, various techniques have been developed to improve pulse contrast, including the use of saturable absorbers and parametric amplification stages. Another limitation of CPA is the potential for pulse distortion during amplification and compression. Nonlinear optical effects in the amplifier and compressor can lead to spectral broadening, temporal broadening, and the generation of unwanted pulse shaping artifacts. Careful design and optimization of the CPA system are required to minimize these effects and maintain high pulse quality. Sophisticated mathematical models based on the nonlinear Schrödinger equation are employed to simulate pulse propagation through the various optical elements, allowing for precise optimization of the system parameters. The reception of chirped pulse amplification was initially met with a mixture of excitement and skepticism. While the potential of the technique was immediately recognized, some researchers questioned its practicality and scalability. The complexity of the CPA system and the demanding alignment requirements presented significant challenges. However, as the technology matured and CPA-based laser systems became more readily available, the skepticism gradually waned. CPA became widely adopted. Donna Strickland and Gérard Mourrou's work built upon a rich history of laser physics and nonlinear optics. The invention of the laser itself in 1960 by Theodore Maiman provided the foundation for all subsequent developments in high-intensity, laser technology, the understanding of nonlinear optical phenomena, such as second harmonic generation and cell-phase modulation, was crucial for developing the concept of chirped pulse amplification. Specific prior work by researchers exploring pulse compression techniques, while not directly employing the stretching and amplification steps, provided important insights into the manipulation of ultra-short pulses. Among those who laid the intellectual stepping stones was Earl N. Dewling, whose work on fiber pulse compression contributed significantly to the field. The influence of chirped pulse amplification on subsequent research is undeniable. Countless researchers have built upon Strickland and Mourrou's work, developing new and innovative applications of high-intensity laser technology, the development of otoscopy science, the advancement of laser-based medical imaging, and the progress in laser-driven fusion are all testament to the profound and enduring impact of chirped pulse amplification. The work of Ferenc Krauss, who pioneered otoscopy pulse generation and otoscopy spectroscopy, directly benefited from the availability of high-intensity, ultra-short pulses enabled by CP. In conclusion, chirped pulse amplification represents a monumental achievement in laser physics, enabling the generation of unprecedented high-intensity, ultra-short optical pulses. Its impact has been transformative, revolutionizing fields ranging from fundamental science to technological applications. While the technique has undergone continuous refinement and faces ongoing challenges, its legacy as a pivotal innovation in 20th century physics remains secure, forever altering scientific and technological landscapes. The story of Strickland and Mourrou's work serves as a compelling reminder of the power, intellectual curiosity, experimental ingenuity, and the profound impact that seemingly simple ideas can have on the world. The subtle irony lies in the fact that a technique designed to prevent destruction has become such a remarkably constructive force across so many disciplines.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.